Hello, everyone. Welcome to our webcast, Improvements in Transformer Winding Resistance Testing. Today, we'll be talking about the various methods used to perform winding resistance testing today, and we will share some testing best practices that will increase efficiency and reduce overall test time. My name is Yerto. I'm the Marketing Communications Engineer for Megger North America, and I'll be acting as the moderator for today's presentation. If you have any technical issues or questions for our presenter during the session, I will be supporting you. On the right side of your screen, you will see a control panel that looks similar to this one. You can start the presentation by typing into the box highlighted. You may also notice that there are two audio options, telephone and mic and speakers. The mic and speakers options uses the voice over IP, so you may experience intermittent audio lag due to bandwidth. At any time during the presentation, you can switch to the telephone audio option. You will receive a copy of the presentation. You can ask questions at any time during the presentation, and I will interject your questions as we have time. Our presenter today is Vince Opedisano, Megger's Product Manager for Transformer Products. Vince is based out of Valley Forge, Pennsylvania. Thank you for joining us.
Oh, you're welcome. Okay, everybody, today we're going to be talking about a subject which has, over the last 15 years, changed dramatically in terms of how often and its significance. In performing testing in the field, winding resistance was considered a more rare test that we conducted as we could, but it was very difficult to do as we did not have the same types of equipment that are available to us today. In looking at this first slide, what we're talking about is not such a simple device as we think of when we see a transformer. The transformer is representative in a very complex or in a complete manner, and the complexity other than the winding resistance which we seek to achieve is shown in the reddish colors. The other components do affect our resistance. We'll talk about some of those methods of improving that, obtaining the results in a. Why we actually test winding resistance is quite clear. It has proven to be a very good diagnostic tool and one that gives us predictive values that we can use in determining the future direction or required maintaining our transformers. We see tap changers especially. This is the only moving stresses, and so it becomes the primary reason we perform, and we will focus on this area as well. We also want to detect or locate partial dead or dead shorted turns. We look for secondarily actually loose crimping, and that's typically after manufacturing, as well as under some strains and stresses that the transformers encounter during operation. See, this is one more usually subjected to by factory, where we're looking for the copper losses of the transformer as they are required as part of the specifications. Winding resistance to measure winding temperature, that's a very common use when we're performing things such as dry out, or in the factory when we want to know the winding temperature once we've heated the transformer for proper cooling down. As well, we now want to talk about the principle of measurement. So when we think of a winding, we think of inductance, and it is the resistance that we care about, but it is the inductance of the winding which is dominant when we first begin the test. As we're applying DC, the one issue that we do have change amps to whatever our test current is, the inductance is dominant until such time as our current stabilizes. And once it stabilizes, then we are left with just and the resistor itself together with the tap connections. And with that, if we have the current and we have the resistance or the voltage, we now are able to determine the resistance. And this is a principle of measurement which many of us are commonly understanding. Well, when we're talking about this, technically what we need to do is we need to change the current to be at 0. So for it to be at 0, we need for the transformer core to saturate. In order for the transformer to saturate, we times seconds. And in the seconds, that is the time that is required. And if you look at this picture in front of you, you will see that the amount of time needed would be higher, as your experience would tell you, based on, in this case, the voltage rating of that transformer. The time to stabilize might be very different from something like a pole top or even any of your small power transformers. We know that the larger the winding, which is reflective of inductance, the greater the difficulty to perform the test. This is borne out by a lot of experience that many of you had in testing over the. Once we do know that we have that, we also need to understand a little bit about what we're testing. And in that case, we want to typically discuss on-load tap changers. So the first type we'll talk about today are reactive type. Now they're designed to take the energy and minimize the amount of current that passes through the winding as we're trying to change the tap. Although many of us think of simple switches, as you can see in the right, some of the mechanisms are complex as they need to be, and they're handling quite a lot of power. And in this case, preventative autos that limit the circulating current when in bridging positions. Without such components, we end up with very high currents, and the high currents can cause damage to both the switch itself. Now, when they operate, it is all dependent on their design and on the needs based on the application. And in this case, they're typically, they run at 0.3 to 0.7 seconds, run slower if the demand is not so critical. When we look at them, but in fact, this is the typical operation. This is a tap changer made by Reinhausen in the non-bridging position, where these devices now handle the current evenly on both sides and then allow the current to flow freely with good operation. But once we go into the bridging position from the non-bridging position, now there's more energies involved. Each inductor in this case has to divide the current, or does divide the current, and so we have a different particular, to see all of this, we can now go to what the particular graph would look like for that particular type of tap changer. Now in this case, what you'll notice is you do not get this nice smooth line that many of us are accustomed to. In speaking about that, and let me take a little bit of time to describe it. When I started doing winding resistance tests on transformers, my first concern was windings themselves. And being new to it, and this was, I guess, about 30 years ago, we looked at the values and compared them only to themselves. So we'd compare A to B to C, and in doing this. But then we found that with load tap changers, that looking at the differences on each, as many as 33 taps, we found it difficult to gauge whether the value was reflective of correct or incorrect amounts. And so we started to graph the results. And many of you do, some of you don't, but if you're not, I would suggest to you that this is a quick way for us to determine the condition of a load tap changer running through transition. This is also useful for offload as well, because we can now tell that the switch itself is not adding any values, any resistances not expected in the ratio turns. And in this case, though, you can see it's a little more difficult when there's a preventative auto to see whether each value lines exactly. When we move into load tap changers, now we've got resistive types are actually in the world more common than inductive types. So in inductive or reactive types, from a worldwide perspective, are about 30% used in the market, whereas resistive is about 70%. And as such, more times we use resistive on tap changers on the high side. It can't be used on the low side, but with higher currents, low tap changers on the low side would be more efficient as inductive or reactive than they would be as resistive. In this case, they do run as fast as active types. Inductors are reactive resistors to limit the current during a tap change. There is, in this case, no bridging position. They do not stop in the middle. They simply go from one tap to the next. And so if you're looking now at the curves that are involved, you can see here that we have a very nice V-shaped curve. Now in this case, there is no, for the nominal, there is no before and after nominal, or there is no, how can I say, there's sometimes a flat spot in the nominal position, and that's when there's a reversing switch is involved. They don't have or a idea. So it's nominal A, nominal B in between. Here, a straight line or a relatively straight line. And in this case, this result is a single phase DC converter transformer, and we only have one phase to deal with. If we had B and C phase to deal with, we would expect that all three phases follow this particular phase. That being said, when load tap changers are positioned on one or another side of a transformer, it typically causes the farthest, let's say, C winding, if it was farthest from the tap changer, would end up being slightly higher than A and B. And this is common. And so the differences, although there is a difference between the windings, they do at least follow this particular curve. Now, when we are testing again with tap changers, we do want to know the condition of the tap. There are a number of modern new methods, which we will not go into today, called dynamic resistance, is in itself a subject which could take easily an hour to describe, to discuss. It is my opinion that dynamic resistance for transformers is in its early stages, and so there are many known entities, many known values, but we are not consistent enough personnel to utilize this technology so much as the staff or the engineering teams back in the offices of the transformer. In this case, I wanted to describe what I first used at a utility that used to be called Ontario Hydro 30 years ago. And in this case, they showed me a small battery, and we're talking the size of a 9-volt battery, a resistor, a light bulb, and the winding. We would take the connection you see here, and then we would run the tap changer through transition. So we would power, and the light bulb would be off, because once the current flows through the winding and everything balances out, it was not a lot of current, then as the light bulb would stay off until such time, or if at such time there was any type of break before make. And if there was, the light would flash. From this, by going back to that position and retrying it and looking for it. Now it did not find all of our issues, but it did find the obvious issues that were not apparent to us when we were running through basic maintenance of the transformer. Today's equipment, at least equipment made by Megger, uses a break before make in similar fashion to what you saw on the previous page, but now we are able to actually perform timing. And in timing, we don't want to actually give you a time, because that becomes confusing for most operators in the field, although we've started to do so early on in this. What we decided to do is give you levels. So we have a low, a medium, or high. And if the transformer has a very good tap changer, one that's relatively well maintained or is well designed, the transition can be set to 5 milliseconds. And we fully, as you transition and you run through the test, that the detector will not turn on, and that threshold is a 10% change for the specific time, in this case 5 milliseconds. Time exceeds, little light will turn on, or a Dixie time. If we were to fail 5 milliseconds, then we would know that 5 milliseconds is not a particular tap changer, or possibly, and this is rare, that the tap changer is totally malfunctioned on every single position, every single phase. We typically think of exceptions when we do this test. And so we would go to the medium sensitivity, which is 20, and then low, which is 80. Now, it should be said at this time, for transition exceeds 200 milliseconds, then the current of the test set, in Megger's case, turns off. For any test set, 200 milliseconds being on or being open would create quite a large voltage, and as such would create or bring damage, potential damage, to the instrument under test. And so we want to limit this type of activity to a known state. And so depending on the age, number of operations, and the type of the LTC, one can change the sensitivity. A typical practice for us is to set it to the highest and see if that tap changer is enabled at 5, and then we run it through all at the highest sensitivity. Once you've done all of this, and in this case they'd set the medium one, you can see where the make does pass. And so this particular transformer did make all or meet all of the requirements for break before make. Now, in order to be optimum in performing winding resistance tests, in order to do it in the least amount of time, one of the key conditions is open circuit voltage. This is from our previous slide, where for saturation, we want to saturate the core. We must saturate the core in order to begin to measure the resistance. To do so, we need the voltage, which is the test voltage, times time. Therefore, and this is why we have it in red, therefore test instruments with higher open circuit voltage require less time to establish flux and saturate the core. This is not a rule that can be changed. And people who tell me that we need more current, I'm not saying they don't, but the first thing that we must have is higher open circuit voltage. So what time do we need to saturate the core? Well, that is dependent upon the winding that you are told. In the cases of windings with very high voltages, we need more time. And so we require this time relative to windings with less voltage. The current is going to be discussed in the next slide, and we will get it of where the importance becomes for the current. So if we look at the actual saturation characteristic as you're saturating the core, and this is on the right, you can see what happens to the current and the voltage as the current goes up, the voltage drops down, and then we reach the saturation where there's a maximum flux, and then there's a particular minimum saturation level, and green. The area we'd like to avoid is in red. And in this case, it's not the voltage that assists us in avoiding this level. This is now related to selecting a test current. So the one rule that we have established, and one that we have tried to get our customers to adhere to, because many of them do call us about the instrument doesn't work, doesn't give me readings fast enough, or in some cases works, but the reading is not consistent on one side versus the other. We follow these rules. The first rule, in order to avoid that red area, is to try to inject above 1%. It's not exactly 1%, but we remember 1%. A lot easier than 0.657 or whatever level we find we need. It's a comfortable level to reach. It's on the higher end, but at least we know that is a goal. The other limit is the 15%. This is as per ANSI and IEC. Now, within our test instruments and within our automation, we don't want to get to 15. We know we can, but we typically set as recommended 10%. And so at 10%, we are well within what should be achievable in performing winding resistance testing in a reasonable time. Unfortunately, some of the typical 0.1 to 15% of rated, and at 0.1 to 1%, that 1%, many of them become disability. And so, if current is less than 1%, measured resistance may not be consistent, and or it'll be stable but then becomes unstable. And this is due to maintaining the saturation of the core, in other words, removing the influence of the inductance continuously.
Hey Vince, I have a question from John. So when comparing between phases, do you also determine the problem?
Yes, we do look for a threshold, but the threshold is guided by IEC and ANSI, and it is set to 2%. That is the limit that we are typically given. But the truth, if a transformer is built with, then one must take a trend ever before and what is it now. And if it maintains that difference, then we know that if it exceeds the 2%, but it was when we first, it is fine. But tip of this presentation, because we looked at efficiencies, 2% is the limit.
Okay, thank you.
Now, you're welcome. Applying large test currents. Now, here is something that most everybody I talk to asks me for more. We would like more current. More current. Why? Because typically people want to do their jobs quickly. Let me say this, that over the years, the time performing testing did not involve winding resistance as it does today. We would only do winding resistance on special transformers, not all transformers. Today, with the advent of the test equipment, we are testing winding all transformers, and as such, sometimes, many times, it becomes the dominant time factor of the day when we're doing our testing. And so we want to get our testing done quickly so as to move on and to be more efficient. Higher test currents do have adverse effects that we need to consider. So one of them is that when we're saturating the core, we have to demagnetize. And the more current one applies, the more deeply one magnetizes the core. And so we do not want to create a condition which is going to be more and more difficult to bring back. Secondly, when testing on the high side windings, it's typically on the high side, the large test currents may actually increase the test time unnecessarily. If we reach saturation and we now exceed it, let's say saturation may be achieved at 2 or 3 or 4 amps, and yet we're going to apply 10 or 15 or 20 amps, then we are going beyond where we need to go to get good, fast, and stable readings. And so we want to think of applying when we apply it. The last one is the obvious one, and that is if we exceed that 15% limit, then we can actually change the winding resistance values over time as the windings warm up or heat up. And as that resistance changes, that destabilizes your circuit until such time as it comes, and that destabilization happens because the changing resistance changes the current and as the DI dt.
Hi, Vince. Another question. Are these currents you are applying DC or AC?
Oh, no, absolutely. They must be DC. A transformer is designed to handle quite a lot of flux AC. They're handling thousands of volts. And they're handling many thousands of amps, in some cases hundreds of amps. And as such, those are all AC. When we perform winding resistance testing, we cannot use AC, we have to use DC. Because otherwise, we're getting the impedance of the winding, and that's bad. We're seeing the impedance, we are not seeing the R, the resistance. The only way resistance is by applying DC current and then letting that core saturate so that all of the inductive effects of impedance are removed and we're left with only. Hopefully that is sufficient for the question. If not, we'll find out. Magnetic flux. So what we have are turns on a core, and in this case we have high and low side. It is optimum, in this case, is to set up the flux in the same direction. And if we do so, we help saturate the core and do so in a manner that removes that inductive effect and now allows us to see the resistance purely. And so what you will see in this case is the direction is coming into H1, and if we were to set it up, comes out of X1, and that would set it up into the same direction. What is more typical for our applications, for the audience here, are three-phase transformers. The single-phase one was just in flux direction. But when you have three-phase cores, it is not the same as just one direction, because as you apply current, in this case from H1 to 0, you will be setting up flux direction from 0 to H2, and also from 0 or neutral to H3. So B and C are running in the other direction. So when we're performing the testing now, this must be taken into consideration. So in this case, in the first case, with the winding neutral, we have both conditions possible. So we can run from 1 to 0, and in testing the winding from 1 to 0, we apply or measure the voltage from 1 to 0, in this case H. As well, if one decided to, if there's no neutral on the particular winding, what we can apply current from phase to phase, 1 to 2, and in this case we can achieve the 1 to 0 value between potential connected to H1 and potential connected to H3. It is a winding which is no current flowing through it, or a bushing with no current flowing through it as well, but we now have reached potentially into what the HO connection sees. And so we can report H1, H0 by using that H3 bushing. As well, if we decided H2, H0, we use that same H3 bushing to reach the values of H. Now, one thing we talked about earlier, and now we're going to expand upon, is trying to keep the flux path in one direction. One thing that if I haven't made it clear, I will make it clear now. As you set up flux, as you apply test current, it's DC, so it has a direction. It flows through the core, so it creates a magnet. If you test the other phases of that winding in opposite directions, the problem becomes you're taking all the energy it took, and in this case, let's say to create the magnet, and now you are applying reverse current. And in applying reverse current, you're actually undoing all the work that was done in your first test and redirecting the core in the opposite way. And in this way, you're actually working harder than you need to. And so we look to optimize that time and utilize the most efficient path for performing the fastest test. There's one other thing that we should consider, and this is the one that is probably the least understood, and the one that if people out in the world are testing delta windings should understand this. As we apply, in this example, current from H1 to H3, we apply at, in this case, let's say 50 volts, and we may be applying 10 amps. As we do so, this particular delta, or any delta, also current, in this case 10 amps, and shares that 10 amps with the H1, H3. So A phase has only 2/3 of the current. B and C phase have 1/3 of the current flowing through them. That is not so bad, but the voltage across H1, H3 is 50 volts, yet the voltage across H1, H2 is half of 50, and the other half going H2 to H3. And so when you're doing this, you saturate A core quickly, but although A is saturated, the current may look okay, but B and C are still going through it. So even though your first reading may be done, B and C are still catching up. And so even though it seems steady, you're going to get these slow changes in A because of B and C. Because that voltage is only half, sometimes it takes a longer time. And so if A is still saturated and B and C become saturated, then it will stabilize. It is under these conditions that we typically want either higher voltage, or what will help us are some higher currents, at least reaching the 1% or 2% plateau. So if we take all of these examples and we look here in the dual, the reason we do so isn't just to saturate the core, but in this case, what we do is we perform 2 tests at one time. Because winding resistance takes so long, doing 2 tests or 3 tests or 4 tests at one time is the optimum way from an efficiency perspective. And here we ground one end. Now, grounding is not critical except under conditions of interference, because we're measuring such low entities, some low voltages, core saturates. And we flow it in the same direction, as you see in this arrow. Just to give you an example of how that looks from a single injection, as you see the black on the left coming in through the red out the black, and then if you're having dual 2 windings in series, then what we want to do is flow them the same so that the flux flows upwards in both directions. One of the areas that we've found recently, I'll say actually it was quite a while ago, but as far as practices goes, we can magnetize faster by using 2 windings in series because of the factor of the turns ratio, not only because of the fact that we're doing 2. And so we get a much bigger, faster effect on most or many transformers by performing a series test. So here we see on a 3-phase core where we actually take, this is a typical construction where the windings are connected in series such that the flow runs in the same direction. Now when you take a delta and a Y, again, we want the core to see flow in the same direction. And so we have set it up here for a delta Y. Common setup that one sees. Y, we're doing some of the same thing. Just different examples. For auto transformers, here now we get to where we are flowing between 1 and 0, and we're measuring X1 to X0. Now, let it be said here, danger in running 2 tests at once, and one that we found out over our experience is the fact that we are not measuring the resistance of X1 to the X1 bushing. Unless there is current flowing through the X1 bushing, we do not know if there's any loose connections from the winding through the bushing to the external world. And so that is a test that we do want to at least do once through that bushing so that we validate that the connections are proper. A little bit complex to understand without a drawing, but that is the case that we've experienced. In this case here, same example where we're running current through H1 out through H3. The H0 bushing has no current flowing through it, reading potential. And so having one reading where current flows through that one bushing is very useful. Now we typically get that resistance when we do our second test in this example, which would be H2 to H0 to H0, including the current flowing through the H0 bushing. Let it also be said here, what we are performing 1 to 3 is because in the core we apply current through the outer phases is a more balanced condition than trying to flow current from H1 to H2. So we typically do 1 to 3 and then H2. That's everything there is what we call a balanced state within the core. And so here are just other examples. And in this case, we have instruments that measure 4 windings. So we can measure all 4 windings at one time. And if there are taps on one side, we simply run all the current through, and then we change the tap OLTC, and then record through as we're wherever we decide to start and finish. Here is a typical connection. This is one of our, in fact, future instruments, but this is a version of an MTO connected to all windings at once. Last topic that we want to talk about of importance, there have been a number of things that we thought over the years as far as how to properly demagnetize. It's been a lesson that we've been learning in some ways the experience, but from the standards it's now clear everyone wants to demagnetize their transformers, wants to do so properly. So today, most of today's equipment have demagnetization features. If not, you should seriously consider that as an important part of it. And in doing so, we want to make sure that we have very good criteria for demagnetization. The old methods, the ones that I've seen at some utilities, in fact, some still use them, and I won't say who, car battery with a switch and a resistor. What we have found in our research, instead of doing 3-phase, which is how we started, that performing a single phase, the center leg, the middle leg, which is, let's say, H2 to H0, is as effective as 3-phase. Now, in our test equipment, because some customers want to test all 3-phase or demagnetize, we have allowed that. Even though it is a sense of stability that people would want, and so we allow that to happen, is better judgment. As well, what we have done, we've learned is that we need to apply more steps. We do not do very coarse steps. We get start coarse and then we run very fine in order to bring the transformer to a closer state of demagnetization done. As a summary, winding resistance measurements are not simple. It is not simply, we do not use AC, we must use DC, and in doing so, we now have the resistance that must be sorted out from the inductive effects of the winding. Important, saturation of the core. That is key to the beginning stages. Volts times seconds is a rule that if you look at a transformer, that you will see that its winding voltage will determine how long it will take you to saturate it. It must be stable before you can achieve readings, and you cannot do anything until that time is reached. So the DC current is very important in this respect, that it have no ripple or minimal amounts of ripple. We have the time constant of inductance over resistance. So if the resistance is very slow, this is the cost that we have in front of us. Delta windings, they are typically the problem child for most of us in testing. And on the low side, a delta plus its low resistance is an issue which require higher current stabilizer. Before break, we can get into fancy dynamic resistance, but the first test we should do is running the test set with DC through LTC operation and knowing that it does or doesn't operate properly in that the test set to flow. And lastly, we're talking about returning the winding. There are many tests that we want to do on a transformer, and if we do winding resistance, we will get effects which may lead us to where we do not. And so that is important on that respect. And so here's a list of some of the instruments that make these tests. And these instruments have a number of those features built into them, as we've discussed. We apply currents in the right directions to optimize the time to give us the most efficiency in testing. And we record everything as we run the test. We can now determine the proper state of a winding and, more importantly, of its load tap changers, and in fact its offload, the DETCs. That is my presentation from this time. Questions? Hopefully I've answered the issue there is. This is an overview. There is much more detail available in any one of those aspects, but it at least gives us an idea on what we can do and how we can improve our testing practices as we conduct them today. Thank you.
All right, thank you. Thank you, Vince. If you have any questions, you can type them in the box now. So we'll start asking some of the ones that we've gotten so far. So Ryan wants to know, is there a temperature standard that we need to cover during resistance?
According to the standards, if we necessary, and if we want to compare trending, that we correct windings, and I've seen two standards. One is 75 Celsius, the other is 85 Celsius. And in all of our forms, all of our instrument forms, and in our automated testing, we provide a checkbox that corrects or does not correct the winding resistance. Regardless of the correction, typically we're looking for the curve, and the curve gives us the critical information that we use, whether that winding can go, or whether that transformer can go back into service for the next 1, 3, 5, or even 7 years.
Okay, so if our test set is capable of anything from 10 to 50 amps, how do we know the best voltage, best current that we need to choose for a transformer of a specific voltage?
So the voltage of the transformer means nothing. And in fact, what we have added to our automated forms lately, and in fact all of our testing, is a recommended test current. So what we have learned is that many customers, instead of phoning us and asking prior to doing the testing, we're going to give them a recommended level. We don't apply it because we let the operator choose, but it's between the 1 and 15% level. And we recommend, or at least in our automated form, 10%. So we try to set it to about 10 needed current of the winding. So a high side winding will be very different than a low, unless it's an so each side will have a recommended level. And if one is higher than the other, it's the lower current if you're running a series test. If you're running the windings in series, high and low, it's the lower current that you must follow as a test setting.
Okay, so another question, if you talked a bit about the reading stability, and then I think on some of our equipment we have percentage stability reading that comes up. So what is the recommended minimum value we should look for? Like 90%, 95, 99.999% before we...
In fact, I've just come back from a conference where that became a discussion point, and I've had this discussion point now enough that it's going to require clarification of some type. What we decided to do about a year ago or a year and a half ago is customers were saying, well, Vince, when do I take a reading? And there are certain levels that we look for. And so here's the first thing. We want a reading to stop changing. And that sounds very easy, but for some transformer windings, that stable number is not so easily achieved. And so we put a little indicator that helps, instead of watching the number, the light will change a color based on your settings. Now the question becomes, well, Vince, when I got the instrument, the light turned green, but the reading wasn't correct, and we find out that their setting, they assume the setting. We all assume somebody knows, but we don't, because every transformer is different. And I could set it very, very high, but then sometimes the stability may not, you may not need to wait so long. And so we have what are two stability of the reading. So if the reading maintains a value over a period of time to within your setting, let's say 99.9, that means that result cannot change by 0.1%, or the light will not turn green. And if so, it'll stay amber or whatever the color is, and as such, when it stays that way for a period of time, 1 second, 2 seconds, and then continues to stay green, your second criteria now kicks in. So if it stays green, and it stays green for your second criteria, which is, let's say, 2 seconds. Well, 2 seconds may not be enough for a very high voltage winding, like 300 kV, 150 MVA, and so now becomes longer. And so what I typically do is to run the winding the first time, especially if I'm doing load tap changers, or winding with a load tap changer, and I'll visually watch how long it takes and time it. And once I get the first time, then I'll know that the approximate time would be somewhere in the order of 10, 20 seconds after I first see the reading appear to be stable. And so I would set 99.8, 99.9 plus 10 seconds or 15 seconds. That means that some windings will require, that's how slowly they change. That's how slowly that saturation happens. And then I do so. Each reading may take 40, 45 seconds, but that is the nature of that particular winding. I hope that's answered it. It's not a clear explanation because it's not a very easy to understand concept. But I typically raise it, the setting, stability to 99.8 or 99.9, and is the before reading. So I would set it, instead of 2, I would set 10 or 15 seconds. And then I get valid readings. And you know it's wrong when your V curve starts to go out of shape. I hope that's answered that question. Not so simple.
Okay. So talking about demagnetization, I have a couple questions. How do we know when the core has been demagnetized? And then if we're putting the unit right back into service after testing, do we really need to worry about demagnetization?
Yeah, in fact, that's here's the conundrum that we will run into. If you worry about demagnetizing, in other words, oh, have I demagnetized? As soon as you try to demagnetize, you are affecting the core. So in other words, by trying to measure the demagnetization, you must demagnetize, because you must magnetize in order to know where the state is in applying a DC. And so our history, our experience tells us that if we're not sure, we simply demagnetize again. And or we've given you the ability to demagnetize all three cores just in case, and we do so in the proper way. Everything we've done in our software is totally automated to our experience and understanding demagnetization. And so yes, there is no indicator for state of demagnetization. Because as soon as you try to measure it, you're affecting it. So you may make it worse, or you may make it better, just by trying to measure the state of demagnetization. Not a simple subject either.
Okay, maybe we'll have time for one last one. Can you perform dual injection on a delta winding?
On a delta-delta? Is that the question? Would they know? Is that because?
Yeah, there's only one delta in the question, so we'll assume whatever you want to assume.
So first of all, when we have a delta winding, we can only test one of the three legs of the delta. We cannot test two legs of the delta. That is not possible in any accurate way that we have figured out, or anyone else to this stage. But to test a delta-delta, when you have a delta-delta winding, and I have seen them as a small number, but I have seen them. In fact, the delta-delta is the most difficult winding to saturate properly, because you have two cores with circulating current affecting each other. As you apply DC to one side, it affects the other side. And so the best way to test the delta-delta winding is in series, one winding to its same phase on the other side. And so that has been our experience, that the delta-delta windings are best tested in series. You don't necessarily need to record the resistance on one side versus the other. Like, you don't have to do dual voltage measurements. You can just get the one you want, but they saturate more completely when you connect them in series.
Oh, actually, Thomas has clarified. He said a delta Y winding.
Oh, yes, absolutely. In fact, if we look at a delta Y winding from some of what we had shown, you're going to test the two phases that are in the same direction. That is the goal. That is the ones that are closest to the same direction. And so in this case, you're going to test here on the screen. You would see both of them going, and they're all flowing in the right way to saturate the core effectively. And this is done where you see here wires. In our three-phase instruments, we do this all internally. We choose it all internally.
Okay. Unfortunately, we're running really close to time, so that would be all we have time for. If we didn't get to your questions, we'll follow up with you individually via email after the presentation. We will email everyone a copy of this presentation in the next few days, and a recording of this session will also be available on our website 2 weeks after the presentation. When we close the webinar, you'll be redirected to a survey, and we will really appreciate your feedback so we can continue to improve future webinar sessions. Thank you all for attending, and have a great weekend.